entity, encompassing every possible trajectory until it finally manifested as a discrete point on the screen. It appeared that the simple knowledge of the photon's path, or even just the potential to acquire that knowledge, was sufficient to collapse its wave-like behavior into a definite, localized particle state. Reality, in a profound and unsettling sense, seemed to care whether it was being watched. This wasn't an isolated fluke, nor a result of experimental error. The double-slit experiment has been meticulously repeated countless times, not just with photons, but with electrons, and even with molecules composed of hundreds of atoms. And the result, without fail, is always the same. Left unobserved, these quantum entities behave like waves, interfering with themselves. Observed, they instantly snap into behaving like classical particles, falling neatly into predictable, single-path trajectories. And if this sounds deeply unsettling to your classical intuition, rest assured, you are far from alone. This experiment lies at the very beating heart of quantum physics, and it stubbornly resists every human effort to explain it in familiar, classical terms. It strongly suggests that at the infinitesimally small scales, particles do not adhere to strict, predetermined paths. Instead, they exist as a sprawling continuum of possibilities, a shimmering, nebulous cloud of potential outcomes. It is only when a measurement is precisely made, when we demand a definitive answer, that this probabilistic cloud instantly collapses into one specific, definite state. Some brilliant minds have attempted to visualize the photon as a wave that somehow splits, traverses both slits, and then mysteriously reunites on the other side. Others prefer the more abstract language of probability, describing the wave function, which we'll discuss next, as a mathematical tool for merely predicting the likelihood of outcomes, not describing an actual physical wave. And still others, notably within the many-worlds interpretation, imagine that each possibility branches off into its own separate, distinct universe, implying an infinite cosmic tree of divergent realities. But whatever the chosen interpretation, the experimental facts remain irrefutable. Until we actively observe it, the particle does not appear to commit to any single, unambiguous state. In the utterly bizarre and profoundly counterintuitive world of quantum physics, if there's one piece of mathematical artistry that gently whispers its influence throughout the entire sprawling theory, like a secret, ancient spell, it is undeniably Schrödinger's equation. Now, please, don't worry for a moment. This isn't about to devolve into a dry, intimidating math lecture. No one, I assure you, is getting out of their comfortable bed tonight to dream about the daunting complexities of partial differential equations. But this particular equation is different. And even though, to the uninitiated eye, it might resemble an impenetrable tangle of Greek letters and esoteric operators, at its profound core, it narrates a remarkably simple story. It describes how a quantum system changes. But let's momentarily step away from the abstract symbols and delve into what truly matters, the core philosophical shift it represents. The key concept here is the wave function, most often denoted by the lowercase Greek letter psi. If that term still sounds abstract or vaguely mystical, try to think of it like this. The wave function is a kind of mathematical whisper, a comprehensive statistical map that encapsulates everything we can possibly know about a quantum system at any given moment. It tells us not where a particle is, but where it might be, how likely it is to be found in a particular location, how it's moving, or indeed, how it might be moving. Crucially, the wave function doesn't furnish us with hard, definitive answers. Instead, it generously provides us with probabilities. If you were to picture a classical particle as a tiny, well-defined dot moving through space, classical physics would allow you to draw a neat, unambiguous arrow, precisely indicating its exact position and velocity at any given instant. Schrödinger's quantum world, however, doesn't operate that way. Instead, it presents us with a hazy, rippling cloud, a probability wave that softly suggests the particle is likely to be over here, but it could also be over there, and perhaps, just a little bit, up there too. This is precisely where the quantum magic truly happens. Schrödinger's equation allows us to mathematically evolve this cloud of probability over time. It meticulously demonstrates how the wave function transforms as the particle moves, though it's really more accurate to describe it as how the possibilities of its position continuously shift and flow like an ethereal current. And then, when we finally perform a measurement, when we, in essence, ask the particle, "Where, precisely, are you?" that expansive, rippling wave function collapses. Suddenly, the hazy cloud of probabilities vanishes, and we are presented with a single, definite, unambiguous answer. Here it is, right there. Now, imagine further that you could write an elegant equation that precisely describes how your mental map of the cat's probable locations changes over time. Perhaps you've noticed the cat tends to move towards corners or prefers to settle near warm objects. That powerful equation would then become your unerring guide to where the cat is most likely to be found next. That, fundamentally, is what Schrödinger accomplished, except instead of tracking elusive cats, he was meticulously tracking the probabilistic whereabouts of electrons. The actual equation itself is continuous and gracefully smooth. It allows these waves of probability to ripple and shift with fluid grace, much like the undulating surface of water in a serene pond. It elegantly respects the fundamental underlying symmetries of nature, such as the conservation of energy and the ceaseless evolution of time. But it does not, in its quantum wisdom, care much for the human desire for absolute certainty. It tells us with stunning precision what could happen, not what will happen. And what remains truly fascinating, even to this day, is how beautifully and flawlessly it works. Physicists have harnessed the power of Schrödinger's equation to describe and predict an astonishing array of phenomena, from the intricate structures of atoms themselves to the precise mechanisms by which molecules bond, from the perplexing behavior of semiconductors to the seemingly magical properties of superconductors. It even accurately predicts exotic quantum phenomena like quantum tunneling, where particles somehow manage to slip through energy barriers that, according to classical physics, they should be utterly unable to cross. The equation itself is timeless, a quiet, mathematical engine gently ticking forward with every passing moment, continually offering us a profound map of the unknowable quantum landscape. One of its most celebrated and foundational successes was its ability to finally explain the hydrogen atom, the simplest and most fundamental atom in the entire universe. Before the advent of quantum mechanics, no one could fully comprehend why electrons, those tiny, negatively charged particles, seemed to settle into specific, discrete orbits around a nucleus, rather than either spiraling inward and crashing into it, as classical electromagnetism predicted, or simply wandering off into space. Schrödinger's equation triumphantly revealed that electrons aren't actually whizzing around like miniature, classical planets. Instead, they exist as stable, three-dimensional standing waves, fixed patterns of probability that describe the likelihood of finding the electron in various regions around the nucleus, defining the very essence of atomic structure. These are the orbitals you may have seen depicted as ethereal clouds or intricate, multi-lobed shapes in chemistry textbooks. Yet, these visual representations are far more than mere artistic metaphors. They embody the profound probabilistic reality of the quantum world, charting the precise, measurable likelihood of where an electron might be found if one were to interact with it. They are not the simple, planetary-like orbits of classical physics. Rather, they are present zones, regions where the electron has a non-zero probability of existing. And their very existence, their peculiar form, stems from the fundamental truth that an electron isn't a tiny, solid sphere. It's a diffuse ripple, a disturbance in a vast, unseen sea of probabilities. It's a concept that is undeniably strange, yet it possesses a breathtaking internal consistency. Unlike some scientific theories that require constant revisions, patches, or explanatory caveats to maintain relevance, Erwin Schrödinger's iconic equation has aged with remarkable grace, maturing like a fine vintage. It simply works. Time and again, it has proven itself capable of predicting the behavior of the unimaginably small electrons, atoms, subatomic particles, with astonishing, almost unnerving accuracy. And yet, for all its predictive power, the wave function, psi, at its heart remains hauntingly abstract. You cannot physically grasp a wave function, you cannot directly perceive it with your senses. But it is there, a mathematical ghost in the machine, meticulously describing the ghostly potential and probabilistic nature of everything, from the atoms swirling in your morning tea to the intricate electronics powering your smartphone. This inherent abstractness naturally sparks profound philosophical inquiries. What is a wave function, really? Is it merely a sophisticated mathematical description of our knowledge about a system, our best guess? Or is it an actual, tangible part of reality, something that truly exists in a state of flux until it is forced by observation to settle into a single outcome? Different interpretations of quantum mechanics, from the widely accepted Copenhagen interpretation to the more exotic many-worlds theory, argue fiercely and eloquently about this very question. But Schrödinger's equation itself, elegantly oblivious to human debate, takes no sides. It simply continues to perform its function, quietly, reliably, and with an undeniable strangeness that has captivated and confounded minds for nearly a century. Even Schrödinger, the very architect of this revolutionary equation, harbored a deep, almost poignant ambivalence towards its implications. While justifiably proud of his mathematical masterpiece, he was profoundly uneasy with the notion that particles lacked definite properties, position, momentum, spin, until the moment of observation. His now famous thought experiment, involving a cat simultaneously alive and dead in a sealed box, wasn't a whimsical musing but a pointed, even exasperated, critique of the very uncertainty and counterintuitive reality that his own work had unleashed upon the scientific world. He provided us with the foundational mathematics of quantum waves, only to then openly question and agonize over what those waves truly meant. Nevertheless, it remains impossible not to admire the monumental edifice he constructed. In a world that so often demands absolute certainties, a definitive yes or no, a precise here or there, Schrödinger offered something far more nuanced and gentle, a shimmer of maybe, a softly pulsing, probabilistic guide to the vast realm of what could be. His equation does not thunder with commands or shout definitive answers. It merely suggests, it flows, inviting us into a deeper understanding rather than dictating one. And in doing so, it unveils a version of the universe that is infinitely quieter, subtler, and immeasurably more mysterious than our classical sensibilities ever dared to imagine. At these infinitesimal scales, familiar concepts begin to unravel. Motion isn't always a clearly defined trajectory. Position isn't always a fixed point. And absolute certainty, once thought to be the bedrock of scientific inquiry, proves to be a rare luxury rather than an immutable rule. Yet, thanks to this one elegant equation, this mathematical compass, we can still navigate gently, mathematically, through the profound haze of the quantum realm. In the classical world, our everyday domain of apples falling, bicycles rolling, and bowling balls colliding, you can know with perfect confidence both where something is and how fast it's going at the exact same moment. This isn't even a question. It's an assumption so deeply ingrained it rarely warrants thought. A radar gun clocks the precise speed of a car, while a GPS satellite pinpoints its exact location. No mystery, no contradiction. But the quantum world, the realm of the ultra-small, utterly refuses to play by those comforting rules. In the 1920s, a brilliant young German physicist named Werner Heisenberg introduced a principle so profoundly strange and so utterly central to quantum mechanics that it continues to give both students and seasoned scientists a genuine moment of pause, a jolt to their classical intuitions. It's known as the uncertainty principle, and its unsettling declaration is that at the most fundamental level of reality, there are inherent, unyielding limits to what we can ever truly know about the universe. Specifically, the principle states this: the more precisely we attempt to ascertain a particle's position, the less precisely we can simultaneously know its momentum, and vice versa. To clarify, momentum is simply a measure of an object's mass multiplied by its velocity, essentially, how much oomph something has in its motion. If you consider this idea in everyday terms, applied to macroscopic objects, the principle sounds almost absurd. How could merely knowing where a train is pulling into the station make you utterly unsure about how fast it's moving? You observe both its location and its speed effortlessly. Easy. But at the quantum scale, the very fabric of reality doesn't permit that kind of absolute clarity. This isn't merely a limitation stemming from our primitive or clumsy measuring tools. It's not a temporary hurdle that can be overcome with better technology or more refined instruments. The uncertainty isn't in our observation devices. It is an intrinsic, inseparable quality woven directly into the very essence and fabric of the universe itself. To illustrate, let's consider the daunting task of observing an electron. Suppose your goal is to simultaneously determine both its exact position and its precise velocity. To do this, you might attempt to shine some light on it, literally, by bombarding it with photons. However, light itself is composed of these tiny packets of energy, photons. When just one of these energetic photons inevitably collides with the extremely delicate electron, it imparts energy and momentum, fundamentally altering the electron's motion and trajectory. It's a bit like trying to locate a tiny, shimmering soap bubble in a pitch-black room by indiscriminately throwing tennis balls at it. You will undoubtedly find the bubble, but in the very act of detection, you will have inevitably, and rather spectacularly, destroyed it in the process. Yet, Heisenberg's profound insight extended far beyond mere measurement disturbance. His principle is not an unfortunate side effect of clumsy observation. It is deeply and intrinsically embedded within the very mathematical framework of quantum mechanics. Even if one could conceive of a hypothetical, entirely non-interfering, ghostly means of observation, a way to watch without interaction, the uncertainty would still persist. It's not a regrettable bug in the quantum machinery. It is an essential, defining feature of reality itself. At the profound heart of the uncertainty principle lies the inherent wave nature of particles, a concept we explored earlier. Imagine attempting to pinpoint the exact location of a single wave in the vast, undulating expanse of the ocean. You can accurately identify the crest of a particular ripple, but the wave itself stretches out, diffuse and dispersed, across a significant region of space. Similarly, a quantum particle like an electron is not a discrete point, but is described by a wave function, a spread-out cloud of probabilities, a smear of potential. If this wave function is wide and smooth, signifying that the particle is broadly distributed, you cannot tell precisely where the particle is, but you can estimate its momentum with a fairly high degree of accuracy. Conversely, if you attempt to narrow the wave function, to concentrate it into a sharp peak in order to pinpoint the particle's position with greater certainty, the wave necessarily becomes more choppy, containing a broader range of wavelengths, and thus a wider spectrum of possible momenta. It's a fundamental, cosmic trade-off, an unbreakable law of nature. There is simply no way around it. Mathematically, the product of the uncertainty in position, delta x, and the uncertainty in momentum, delta p, is always greater than or equal to a tiny, irreducible number. Planck's constant divided by 4 pi, delta x delta p greater than or equal to h/2. This value, Planck's constant, is extraordinarily small, which explains why in our macroscopic, everyday world, the effects of this uncertainty are utterly negligible. You can measure the position and speed of a baseball or a moving car to an astonishing degree of precision without ever brushing against these quantum limits. However, at the scale of electrons, individual atoms, and their subatomic constituents, this intrinsic uncertainty becomes not only significant, but utterly impossible to ignore. It fundamentally shapes the very behavior of the world that lies beneath the threshold of our senses. If you attempt to trap a particle within an exceptionally small space, to nail down its position with extreme precision, it doesn't simply stay put. Instead, its momentum becomes wildly uncertain, causing it to zip around unpredictably with immense energy. The tighter you try to confine it, the more violently it resists, as if nature itself recoils from being forced to reveal too much information simultaneously. This isn't an error in our observational instruments or a quirk of particle behavior. It's an inherent blur that simply cannot be wiped away. One intuitive way to grasp this is to imagine trying to hold mist in your hands. The tighter you clench your fingers, the less mist you actually retain. It slips away. Open your hands just a little, and more of it seems to linger, a gentle, diffuse presence. The uncertainty principle creates a kind of built-in, intrinsic resistance, a gentle but firm pushback against absolute confinement.